Hello, let me introduce our paper, Mitigating Background Shift in Class-Incremental Semantic Segmentation. The goal of class-incremental semantic segmentation is to avoid forgetting previously learned classes when learning new ones. For example, the model should progressively learn classes like sofa, dog, and person while retaining knowledge of earlier classes. One key challenge is background shift. Pixels that belong to old classes, such as dog, are often mislabeled as background when the model learns new classes like person. This mislabeling leads to forgetting old classes or confusion between the new and background classes while learning new ones. Traditional pseudo labeling and knowledge distillation rely on an old model. However, this method often mislabeled pixels as background, leading to a performance drop in recognizing previous classes. Our approach addresses this by selectively detecting objects and ignoring mislabeled pixels during training. In background weight transfer, the background weight is duplicated to new class tokens to help the model learn new classes. While useful, this can also create confusion between new classes and the background, leading to background shift. Our method addresses this by decoupling new classes from the background through a separation objective. Our framework tackles background shift with three key components: selective pseudo-labeling, which handles ambiguous pixels, adaptive feature distillation to focus on reliable feature transfer, and a separation objective to clearly distinguish new classes from the background. In traditional pseudo-labeling, the model assigns label based on prediction from the old model. However, traditional pseudo-labeling misclassifies ambiguous pixels from old classes as background. In selective pseudo-labeling, we address the issue by assigning ambiguous pixels an ignore label during training. The process starts with prediction from the old model, which are used to calculate the object identifier. This identifier checks whether the combined score of all object classes is higher than background score. If it is, the pixel is classified as an object. By applying this object identifier and priority merging, selective pseudo-labeling prevents old classes from being misclassified as background. Adaptive feature distillation uses a reliability map to distill only reliable features. The map is created based on three conditions. Pixels from old classes are given a value of 1. Pixels from new classes or ignore labels get a value of 0. And pixels classified as background use the confidence score from the old model. This helps prevent background shift by focusing on reliable areas. To address the issue of background shift toward the new classes, we use two techniques: label-guided knowledge distillation and orthogonal loss. Label-guided knowledge distillation actually works by distilling the old model's refined logits, transferring the background logits to new classes when necessary. This helps decouple the new classes from the background. Orthogonal loss goes a step further by forcing the weight of the new class to be orthogonal to the background weights, ensuring a clear separation between the new class and the background. It also involves separating the new classes from the old ones to mitigate the background shift toward the new class. In our experiments, the scenario involves learning initial set of classes, such as 19 or 15, followed by incremental learning of 1 to 5 additional classes at a time. The overlap setting includes both current and future classes, increasing the challenge, while the disjoint setting includes only current and past classes. Despite the difficulty of overlap setting, our method achieves state-of-the-art results, especially in the 50-to-1 overlap setting scenario. Our approach consistently outperforms others, indicating our superior handling of incremental learning. The ADE20K dataset presents a much more challenging scenario than Pascal VOC, with 150 classes compared to 20. Despite this increased difficulty, our method still achieves state-of-the-art performance. This is particularly notable in challenging multi-step scenarios such as the 50-to-50 and 100-to-5 settings. Our method handles both large and small incremental class learning effectively, proving its robustness and adaptability. In this qualitative analysis, we compare our method with a previous model and a baseline that used traditional pseudo labeling and distillation techniques. The results show that our method significantly outperforms both approaches in retaining knowledge of older classes while learning new ones. Thank you.